Well, good morning. It's 9:31 on Tuesday, the 27th of September, 2016. It's supposed to be Math 238, Applied Differential Equations, I believe is the name of the course. And I'm the only one in the room, which is not a good sign. I hope some others will be coming in soon. I hate talking to myself, but I guess I will until someone else shows. I forgot to open my graph paper, but here it comes, and plain sheet 2. It takes a while for PowerPoint to open. Sorry about that. I didn't have this done already. And we'll do the slides from current slide. And we wait till the black screen disappears, and then get out of presenter view, and then get into a more useful view. Well, I'm used to doing it 3 times for projector, which no one's in. I don't have the projector on. All right. Now, where we left off last time, I would ask if there are any questions, but since there's nobody here, we're looking at exact equations, and this includes some partial differentiation and partial integration, which unfortunately you haven't had yet if you haven't finished Cal 3, and I think most of you are still in Cal 3. And what is this coming in the door? Maybe a student? I can't tell. But we'll go over whatever you need to know about partial differentiation as we get to it. Now, when we finish page 63, which we just barely got started, we were talking about in the special case when some function f of xy is equal to some constant c, then this implies that you can write a differential equation. Okay? And we did that at the bottom of page 63. Top of 64 starts, in other words, given a one-parameter family of functions, f of xy is equal to c. Let me get my pen activated. Okay? Yeah, there we go. Sometimes it works and sometimes it doesn't. Given a one-parameter family of functions, f, this is such a pain, of xy is equal to c. Okay, some function of 2 independent variables is equal to a constant. We can generate a first-order differential equation by computing the differential on both sides of the equality. And here's their example. Okay, x squared, that's your x, or one of your x's, minus 5xy plus y cubed is equal to c, some constant c. One parameter family of equations. Okay, now, when we're doing taking a differential of both sides of the equation, let's first do the terms that have x's in them and the terms that have y's in them, and one of these terms has both, so we take a differential of whatever's there. In fact, I'm going to do it in gory detail. They sort of skip some steps here. Let's take the derivative of the first term, okay? Differential of the first term. That would be 2x dx minus, now we're going to take the differential of this. If we took the differential of that first term with respect to y, it would be 0 because there's no y dependence there. So we're not going to do that. This one we take differential with respect to x, that would be a minus 5y dx, taking the derivative with respect to x, but we also have a minus 5x dy because you take the differential with respect to y as well. And then the third term only has y, so that would be plus 3y squared dy. And take the derivative of the right-hand side, that's a constant, that would be 0. Okay? Okay, if you combine your dx's together and your dy's together, this gives you 2x minus 5y dx minus, they put a plus here, which is fine, plus a negative 5x plus 3y squared dy equals 0. Okay? Now you could have done a minus. Okay. Good to see. Were you here a little earlier? Oh, okay. The door kind of opened, and I thought, is someone there? All right. Cameron showed up. Okay. And Victor showed up. Okay. Glad y'all are here. I hate talking to myself. Okay.
But you do it anyway.
I do it anyway. In fact, let's now turn on projector and flip the light deals here. Just a little bit for the come up. I've been telling all the classes that last week, and actually it was the week before last, I missed it. The vice president sent around a memorandum about removing unpaid students from the class, from classes. The good news is this class wound up with no unpaid students. Okay, the one we thought was unpaid, she had been unpaid for a while. Hers finally came through. The sad news is we haven't seen her since then either. So hopefully she'll get here. But if you run into friends or others who have been not being allowed to go to classes because they didn't pay, this is the earliest in the term I can recall them doing this, but they have done it now. So there may be some type of talking your way out of it and getting back into the class if you get your payment made, but I'm not sure on how those procedures work. Sorry. Okay. The rest of this, just encourage you to consider tutoring, new bookstore hours. Encourage you to consider joining the math team. It's a lot of fun. I think you'll find it helpful, beneficial. Bookstore will be closed Thursday and Friday, and my office hours are modified Thursday and Friday because I've got interviews on the Birmingham campus. And Blackboard starting next Friday, not this week, but the following week, October 7th, every Friday afternoon from 3 to 5, Blackboard will be down, okay, for maintenance, every Friday. And then coming up, the second week in October is the Miss Boston State Coronation. The theme is the Harlem Renaissance, a salute to Harlem, and that will be, they'll open the doors sometime probably before 6:30. They're having a costume contest type thing. It's beginning judging at 6:30. The actual event starts at 7, just next door at the Bessemer Civic Center. And this is a new announcement. Imagine most of you are already far enough along that this isn't a concern for you, but if you happen to have not completed your Humanities and Fine Art elective, they are now offering theater as an option for that Humanities and Fine Arts. If you are currently taking Humanities 101, Art 100, or Music 101, you can get extra credit for this if you become part of the community theater production, and you'll get extra credit for that class. For more information, you can contact Mrs. Rebecca Duncan, who's in this building most of the time, down the half flight of stairs, just past room 254, next office on the right is Miss Duncan, right before you get to Dr. Thomas's office. Okay, those are the announcements for today. I've got y'all marked here, and I was going over this at the top of the page. They sort of skipped a few steps there, but this is a differential equation written in sort of a different form from what we're used to. Obviously not a linear differential equation, mostly because of this right here. You have a 3y squared in the term with your dy. So that would be difficult, if not impossible, to get out. Certainly your original function isn't a linear function in y either, though it would have to be, but it definitely isn't. So I carried out a couple of extra steps there, showing how they got to the stuff they got to at the top of page 64. Now they follow that by a definition. Of course, not every first-order differential equation written in differential form, like this one, and here is the generic form of this, m of xy. Notice this is your m, that function that happens to be a linear function in x and y, dx plus n of xy, and this isn't a linear function, but it is a function of x and y, dy equals 0. You can make up some functions that fit this bill that you can't possibly solve. Not every first order differential equation written in differential form corresponds to a differential of a function f of xy. This won't necessarily produce that. Okay, any of these will produce something like this, but this won't necessarily produce that. You won't always be able to go the other way. So, for our purposes, it's more important to turn to the foregoing example around, namely, if you are given a first-order differential equation, such as this one, okay, then can you guarantee that you can take its derivative? Well, obviously did, because we started with this and we carried it. And basically what we did a d of this equal a d of that, okay? We took a differential of both sides and we produced this. Now the question is, if you're given this, can you guarantee you can get back to one of those? That's what we're going to be doing, okay? So here's the definition of an exact equation. And since I still don't have a book, let me write this definition down. All right. A differential expression, m of xy dx plus n of xy. This is the craziest thing to write on, okay? dy is equal to 0, okay? There's your, well, actually, the expression doesn't have to have the equation, so let me take that out. Wondered why they said expression, not equation, okay? This is an expression, differential expression, okay? This differential expression is an exact differential. That's what we call it. Okay. It's an exact differential in a region R okay, of the xy plane Okay, now, what we mean by that, obviously m's a function of x and y, n's a function of x and y, so this is based on some region, you can think of it as your domain, in the xy plane. Now, maybe not everything in the xy plane is there, but certain values are. This could be an odd shape down there, it could be the entire plane, it could be half a plane, a portion of a plane, it could be anything, but it's a differential in some region R of the xy plane if it corresponds to a differential of some function f of xy. Defined in that range R, region R. In that region R. The first order differential equation has the form of this thing here, m of xy dx plus n of xy dy equals 0. Okay? And it's said to be an exact differential, like what we started. It seems like we're writing this in circles. Okay? If the expression on the left-hand side is an exact differential. Boy, it's saying it is an exact differential if there's some region there, and this is called an exact differential equation if that forms an exact differential. I mean, how circular can you get here? Okay, but really this is making, I hope it's making more sense than what you do. So here's another one. I'm going to, because I'm not sure we got that much out of that definition, but that's not really very fair. It is a correct definition. Here's an example. X squared y cubed dx plus x cubed y squared dy equals 0. Okay. That is an exact equation differential equation. They don't always say that. They just say exact equation, but I like reminding you it's a differential equation. Because its left-hand side is an exact differential of what? Okay? Well, you notice when you did a derivative of the first thing, you got an x squared. So this means it must have had an x cubed, and the y cubed wouldn't have been changed any. Well, we've just taken the derivative. I don't want to do that. This is better. Okay. But we would have needed something else, and that something else would have been a 1/3. Okay. What's that? 1/3. That certainly will take care of the first one, but then if we take the differential of this with respect to y, again you get 3 times 1/3, which is 1, x cubed y squared, and that's exactly what you get there. So this is your exact differential equation. Now this one though could be equal to c, some constant. Okay. Okay, because the I'm going to take out that C for just a moment here because I want to do more with it. What we've got here, the exact differential of this thing is that thing, okay? Because you take the differential of this, first with respect to x, and you get 3, you get x squared y cubed dx, and then take the differential of it with respect to y, and you get x cubed y squared dy. And that's exactly what you've got there, okay? Because it is an exact differential. Notice that if we make the identifications that this is your mx, m of xy, and this is your n of xy, okay? And then, now, this is the part that we talked about last time. Here is the key. Here is the test. Take the partial of this with respect to y. Not x, but with respect to y. Okay? Now, again, y'all haven't had, have you had Cal 3? No, you're in it now. Okay. If you did this, partial of this with respect to y, that would be the partial with respect to y of x squared y cubed. Okay? Now, remember how I said we do this? The x, because you take it with respect to y, you count x as if it's a constant. So that would be
3y squared.
3, no, you don't, okay. You count it as constant, you don't throw it away. 3x squared, y squared. Okay? But you, no, so you just take it with respect to y, just with respect to y. And then you take the partial of n of xy with respect to x, okay? And if you do that, this will be the partial of x cubed y squared with respect to x. What would that be? 3, I'd say x squared y squared, but that's fine either way. Worked. And guess what?
I put it up.
Right. Right, yeah, you take it as a constant and put them together, okay? Exactly. But those are exactly the same. So here's the test. If you can do this and they come out the same, then it does have an exact derivative, exact differential. Okay? If you can't, it doesn't. Okay? So don't worry with it. Don't mess with it. It just doesn't have an exact differential. Okay. So that leads to theorem 2.4.1, which will be it's a criterion for exact differential. Let m of xy, this is so, and n of xy, okay, be continuous, okay, and have continuous first partial derivatives, and have continuous first partial derivatives. Okay, ugly abbreviation. In a rectangular region. Now here they say a rectangular region. I don't think it really has to be rectangular, but for this definition it's fine. And that rectangular region R is defined as by A is less than X is less than B. You could put equal signs in there, but you don't need to. C less than y is less than d, okay? Then a necessary and sufficient, okay? Now you'll see those show up together. Necessary and sufficient. That's sort of like if and only if. That's your double arrow. Necessary and sufficient. It's necessary for this to be, but it's also sufficient for this to be. If this holds, it's got to be true, okay? So we'll use that term. That period. Then a necessary and sufficient condition for that m of xy dx plus n of xy dy be an exact differential is that, and here's the necessary and sufficient condition, exactly what we did before. The partial of m, which is a function of x and y, with respect to y, is equal to the partial of n, which is a function of x and y, with respect to x. Okay. Now, notice here is m of x, y, m of xy dx plus n of xy dy. Those are the things there. But you take the partial of m with respect to the other variable and take the partial of n with respect to the other variable. So then the one your differentials for. Okay. What's that? Well, yeah, but that's what makes it work. This being the function, that's the functional coefficient of your differential with respect to x, you take the partial of that with respect to y, and this functional coefficient of dy, you take the partial of that with respect to x. And if those are equal, then you can do that, and that gives you an exact differential. Okay? Otherwise, they don't. That's what it means, necessary and sufficient. Now, one reason they phrase it that way is you have to prove the necessary part, and the sufficiency part, you also need to prove they don't go about doing it. So, let you do. But that requires more information about partials, and let's just take it at face value now. Later, when you, in Cal 3, when you get the partials, I think you'll sort of, if you remember this, see the connection. So, let's now look at a method of solution. Given an equation in differential form, that's this thing here equals 0. Okay? That's your equation in differential form. Okay? Determine whether the equality from 4 holds, this thing, okay? And if it does, there is a function that when you take the partial of that function, you get m of, with respect to x, you get m of xy, and calculate that by integrating. Okay. All right. There is a function, f, so when you take the partial of f with respect to x, you get m of xy. Okay? Now, how do you do that? You kind of write it in differential form. And it doesn't seem right, and I shouldn't. Let me keep the partial there. F of the partial of f, okay? Now, remember f is a function of x and y. Okay. All right. is equal to m of xy dx. And since I'm making that a d, I'm going to go back and make this a d too. I'm sorry. It just doesn't feel right having a partial there. So, okay. Okay. I mean, you're only taking with respect to that one variable. You're treating y as if it's a constant. So therefore, it is only a function of x. Okay? Because everything is with x here. Well, what you do here is integrate both of these, and that comes up with some. Let me go over here. I don't know. It doesn't like it there. What's that?
In other words, it is because it is.
Kind of, yeah. If you take a integral of a differential, you get the function f, and it is a function of x and y, but y right now is treated as a constant. And you integrate this only with respect to x, treating y as a constant, okay? And that gives you some value, okay? But y is a constant, okay? So whereas normally we do a plus c because this is an indefinite integral, right? But now y can be a constant, so yeah, so this could be plus some function g of y. No x's in it, and there may not be any y's in it, but it could have y's in it because y is counted as a constant, and certainly there could be constants in it, whatever, okay? So that gives you that. Now, where the arbitrary function g of y is the constant of integration because you're integrating only with respect to x, so it can't have y's in it. Now, what we do is take this thing and differentiate with respect to y. So this one gives you the partial of f, that is a partial, because that's a function of x and y, with respect to y, okay? And that's equal to, okay, the partial with respect to y of this integral. Okay. This thing is so aggravating. Plus g prime. That is a complete derivative. It's not a partial derivative because g has no x dependence. This has x dependence, this has x dependence, this doesn't. So when you take the derivative of this with respect to g, that is a regular derivative, not a partial derivative. Okay. Now, before you get too excited here, a derivative of an integral doesn't necessarily get you this back. Remember? Because this is with respect to y, that's with respect to x. So don't go around removing that. Right. But this is a lot more confusing than it looked. If you actually did the integration, you just have a function. It's just we don't know what the function is, so we have to leave it in integral form. But you have a function, then take the partial of that with respect to y.
So when you take the partial of both sides,
Right.
partial derivative with respect to y,
Right.
you still get a g prime.
Yeah, a dy dx, a dg dx here. But I mean dg dy here because this has no x dependence. The partial's only if you have both variables. This one by definition can't because that's your constant of integration. Y is counted as a constant when you're integrating with respect to x, so therefore, you know, you have to include the possibility there. So this is a prime. dg dy. That is not a partial, it's an absolute. Okay. All right. Actually, real functions are a lot easier than keeping all this symbology in here. Okay. Now, you have all that, and if this is equal to, I'm out of room and it keeps blocking out on me if I do it there. If this thing that we have here is equal to your n of xy that you have here, then you are in good shape. Okay? If the partial of f, whatever that function is, with respect to y is your n of xy, then you have an exact derivative. Okay? Well, let's see what that would imply then. Okay? That would imply if this thing's equal to that, then that would imply that g prime of y, whatever that was, is equal to n of xy minus this integral, partial with respect to. I'm too near the bottom of the page. It's not letting me right here, and that's why I hadn't done that. Yeah, I should have started a new page earlier. Let me. Where's that?
All the words.
All the words? Okay. I should have just. But this is what we're trying to show. So I'm going to leave that in there. But I'll get rid of all the rest of the words. And, since I erased the top part, I might as well erase the bottom part too. Okay, I'll leave that too. Okay, let's go back to my pen. Ooh, let me go back and erase this. Because I can't write down here anyway, rather than leave it. So let me write that part up here. So your G prime, and G, I guess so. G prime of y equal to n of xy minus partial with respect to y of the integral of m of xy dx. Okay. All right. Now, if you now integrate this with respect to y, okay, because this is dg dy, okay, so I'm writing this in differential form, snicker, snicker, okay, all right, is equal to n of xy, let's see, I'm going to go on and put my dy here, minus the partial with respect to y integral of m of xy dx, and then dy here, okay. This is truly rather strange looking. And they say in a few words and skip all the work, and I think I'll skip the work too, but because we're basically have almost no room left, this comes up with some function of x and y equal to some constant c. Okay. If you plug that in, substitute, blah, 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 blah. Okay.
People probably understand
Yeah.
better the example.
Absolutely. Okay. But what the whole, they summarize this at the very end. In either case, none of these formulas should be memorized. In other words, you don't have to go through all this. This is justification for it. When you're really working with the functions, it comes out a lot simpler. So I'm going to erase all this. And let's do the example. Here's what we got. Solve this. 2xy dx plus x squared minus 1 dy equals a 0. Okay? That's what we're trying to solve. That's a differential equation. It's not a linear differential equation.
So, do we want to start by taking the partial derivatives of 2xy and the other side?
Yeah, that's where we're going to start. In fact, I just said it wasn't linear.
It looks linear to me.
It sure looks that way, except that what you would have to do is divide, write it in derivative form, dy dx
And be what?
times this thing.
X squared times y?
Yeah, okay, now, leave that alone with this. X squared minus 1 dy dx plus 2xy is equal to 0, okay? Well, sure enough, that is linear in that term, and you can divide then everything by x squared minus 1. Now, the only problem with that, x can equal plus or minus 1, but it really would make no sense for it to anyway. So yeah, this is actually, could be written as a linear differential equation. But we're going to pretend it isn't and just see what happens here. Oh, it's an easy example, okay? So let's do it, okay? First thing you do is identify this is your m of xy. This is your n of xy, okay? With that in mind, what you want to do is do your partial. Partial of m with respect to y, and see if that's the same as the partial of n with respect to x, okay? Well, let's do the partial of m with respect to y. What would that be?
So,
2x, okay? And do the partial of n with respect to x, and you get 2x. These are indeed equal, so this does have an exact derivative, okay? An exact differential, okay? So, that just shows that it does, okay? Now, it is exact. That means there is a function, f of xy, okay? There is one. You know there is, such that the partial of f with respect to x is 2xy, and there's the same thing, f of xy, such that, well, okay, the partial of f with respect to y is x squared minus 1, okay? That has to be the case, okay? Now, what you do to this one is integrate that with respect to x, so that would be f is equal to, okay, let me do it this way. Derivative of f we're writing it that way now, is equal to the integral of 2xy dx. Treating y as a constant, okay? And what does that give you? Y is a constant. You could pull it outside if you wanted to. Well, you have a 2 there anyway, so that just makes it x squared y, right? Plus some other g of y. Constant of integration, except it could be a function of y. Okay, so this is what your f would be. Okay, now we want to do the same thing here and take the partial of that with respect to y. So partial of f with respect to y, and what would that be? Okay. Take the partial of that. Partial of that right here with respect to y. X squared, okay, plus g prime of y, right? That's an ugly y. Goodness gracious. Okay, g prime of y. Okay, but this thing is supposed to be that. The x squared is fine, so this says g prime of y has to equal a minus 1. So what would g of y have to be? Negative y. Okay? So, what then your f is? Whoa, don't do that. Okay. What your f then is, f of xy, okay, is equal to x squared y minus y. Okay? And I guess you could put a plus c in it, do they? Yeah. No, they just do it like that, okay? So the solution of the equation in explicit form is then this thing equal to some c. X squared y minus y is equal to c. That's your constant, that one parameter form. Second?
So instead of saying it's equal to f, it's equal to c?
Well, no, that's what the f is. At the very beginning, we said f of xy is equal to some constant c. There's your f of xy is equal to some constant c. Now, this one, like we said, could have been written as a linear equation, not in x, but in y. Factor out a y, and you have y times x squared minus 1 is equal to c. So y is equal to c over x squared minus 1, which is what we would have gotten had we solved this as a linear equation. Okay? So this one you could actually get it explicitly. A lot of times you can't. This one you could, because like I said, it was a simple equation to start with. This form is called an implicit form. This is called an explicit form. You'll always be able to get an implicit form if these things work. If those are the same, you get an implicit form. Occasionally, you can write that explicitly y as a function of x too. Not always, but sometimes. Okay. That probably meant you could have done it a different way. So, note the solution of the differential equation in example 1 is not f of xy is equal to x squared y minus y. Rather, it is f of xy is equal to c. Okay. If a constant used in integration g prime of y, then we can write the solution. If a constant is used in the integration of that, then we can write the solution that f of xy is equal to 0. That phrase hardly makes any sense. Note, too, that the equation could be solved by separation of variables, and that's what we said early on. We could have done it, but we didn't. Okay. Most of the time, if we can, that's the easier way to go. But they were trying to show this technique. So guess what? Let's do one that can't be, okay? So let's come down here. Have y'all got this, what you need? Okay. So let's do this one. Solve this. E to the 2y. Anyone want to doubt this is not a linear equation in y? Minus y times the cosine of xy. Ew. Okay. Dx. Yuck! Okay. Plus 2x e to the 2y minus x cosine xy plus 2y dy is equal to 0. Right down. All right. Solve that. Yep. You name this to be your m of xy. This is your, this whole thing here is n of xy. Okay. Partial of this thing with respect to y. Okay. Okay, we'll do that in a second. Let's do that one. What do we get? Second? Okay, you certainly have an e to the 2y in it with a 2 in front, chain rule. Okay, that's the first one. Minus it's a product rule. Yeah. Derivative of the first times the second, cosine of xy. Second, plus, okay. Y, why not? Okay. I think there's an x in there too. Sine of xy. Right? A constant, exactly. Chain rule again there. Okay. So you have the first times derivative of the first times the second plus, well, it's, the first times derivative of the second, and derivative of cosine is minus cosine is sine xy, but then derivative of that with respect to y would be x. So that's why you get the other x. All right, so there's your partial with respect of m with respect to y. I don't know if we've got room. Let's try it. The partial of n xy with respect to which? X. Okay, and what does that give us? Okay? Wait just a second now. Taking the partial with respect to x, you count the y as a constant. Okay, y is a constant, so 2y is a constant. E of a constant is a constant. So basically, you have a constant. 2 is a constant. So 2e to the 2y is a constant times x. A constant times x is just a constant.
2e to the 2y.
Right. It would be 2e to the 2y. You see it? The only thing you take in a derivative with respect to is the x. All the rest of that is counted as a constant. When you take the derivative of constant times x, you just get the constant. That is the constant, which is good. Okay? Shouldn't be looking there yet, but that's good. Okay, that's the first term. Next. Second? Yeah. Second?
Yeah, it is another product.
Yeah, it is.
That would be cosine xy, right?
A minus cosine xy? Is that what you're saying?
Yeah.
Yeah. Okay. You derivative of the first times the second. Okay.
Plus.
Yeah. This will be a plus. Would have been a minus, except the derivative of cosine is a minus sign. So that would be a plus. X. Y. Why not? Sine xy. Okay. What's that? That's it, because the partial of 2y with respect to x is 0. Exactly. Okay? And sure enough, these two terms are the same, these two terms are the same, and those two terms are the same. They don't look the same, but they are. It's the xy or yx. It doesn't matter which you call it. Sine of xy or yx. It doesn't matter which way you call it. So, sure enough, they are true. All right? So what do we do with that? What's that?
I said since matching isn't an option.
Okay. Probably not a bad time to say, let's assume that there is an f such that that's what we're looking for, the f of xy, so that the partial of f with respect to x has got to equal that m. Okay? So, okay, so the way to do that is f would then be integral of m. So you have to integrate this, okay, with respect to, let me write it down, e to the 2y minus y cosine xy dx. Okay? All right. Notice this is just a constant. So that is going to be, and I'll have to write it here, e to the 2y x. Antiderivative of a constant is constant times the function. Right? Okay? Now the next part. Okay? The y can come outside. In fact, let's do that. Minus y times the integral of cosine xy dx. Okay? Now again, y is a constant. So what do you have here? Antiderivative of cosine is
a negative
sine.
sign? No.
Okay. So this will be, this term stays the same, e to the 2yx minus y times sine of xy.
Where did the x come?
Huh?
The x after the e to the 2y?
Okay. This is a constant, right?
Yes.
I sort of did this. I put a dx with this and a dx with this. Did another integral. Okay. Integral of a constant, dx, is going to be cx, right? Well, this is the constant is this.
Okay, and then,
Yeah.
okay.
Yeah.
See, I thought you just pulled it out and didn't realize you had actually taken the integral of that.
Right.
Okay.
Now, I haven't finished integrating this. The minus y is out here. Antiderivative of cosine xy is sine xy, but you have to sort of reverse chain rule type thing. You're taking with respect to x, so this y is a constant, so you need a 1 over y here for that to be the right thing, right? Okay, so your 1 over y wipes out this y. Okay, and then we have plus some g of y, some other function of y. Okay, so that is our f. Okay, then we take the partial of this thing with respect to y, and that's supposed to be our n. So let's do that. The partial of this thing f, this f right here, with respect to y. Okay, and what does that give us?
Y is now a variable.
Mm-hmm.
So you have 2e to the 2y?
2x e to the 2y.
Oh, you just pulled the x out.
Yeah, because x is the constant from this now. X is the constant, y is the thing we're taking the derivative with respect to. So x is a constant and 2 is a constant. So it'd be x times e to the 2y times 2. Okay. First part done. Second part. Minus x sine of, no. Derivative of that. Cosine, yeah. Whoa, wrong place. Okay. This was the sine down here, and this is the cosine up here, xy. Okay? Huh?
G prime of y.
Yes, plus g prime of y. Got it. Okay. Now this is supposed to be our n. Well, this part is hunky-dory. I like it. This part is hunky-dory. I like it. This says that g prime of y is equal to 2y. Right? This thing has to equal that. So what would y have to, what would g have to be? Y squared.
It would have to be, G prime would have to be y squared, or no?
Yeah. Plus g would have to,
G would
okay.
have to be 2y.
Okay,
So
yeah.
take the derivative of that, it would be,
Yeah, the g prime has to be your 2y. Right? That's what I wrote here. G prime has to be that 2y. And you integrate that, or dg dy, integrate that, that has to be y squared. Plus a constant. Okay. Well, we're going to take the constant and put it at the end. But this then is your f. So let's write the exact thing. F of xy is equal to e to the 2y x minus sine of xy plus y squared, okay, and you set that equal to c, and that is your differential equation. I mean, that's your solution for your differential equation. It's one parameter solution. Huh?
You get sine. Wait, where are we at?
Okay. Well, you could go any place you wanted to. Here was your F with the G in there.
See, I thought it got flipped over to cosine.
Okay. When you took the derivative of it, you did.
Right.
See?
Right there in the middle,
Yeah. I know it's somewhere here.
where all the arrows are pointing from the
Yeah.
middle to the
Yeah, and this is indeed, yeah, this is your partial with respect to y. That became that. So you go back to your F, and that's that plus, and your G that you found out there was y squared. So that's your exact solution. F of xy is equal to some constant c. Okay. Now, how did they get a 0 there?
They just kept the C on the side of the equal sign.
What's that?
Well, it started out being equal to 0, right?
Right.
And they just kept the C on the side.
Yeah, but you always had the m dx plus n dy equals 0. That's always the case.
It would no, because then if you subtracted it over, it equal negative C. But I mean, that's still C.
Okay. Now they called theirs h, not g. Okay, so sorry about that.
They took it with respect.
So h prime. No, wait.
We did G of Y, they did H of X.
Oh, I'm sorry. They've just put the c. Okay, I'm sorry. I didn't see that. I put equal c. They put plus c equals 0.
It's the same thing. Because if you subtract the C over,
Yeah.
it's still C.
Yeah. So same thing. I don't know why. I mean, my c is the minus of their c, but it's the same thing. It's just a constant. All right. Now, how do you get rid of the c? If you have some condition, initial value, boundary value, some sort of value. That's what the next example is going to be. So it's all right to erase all this. Okay.
Today is registered to vote day.
Oh, is it? I wish I'd have known that. I'd have been announcing it to all my classes. Because all these folks. I hope you're registered, right?
I've been
Okay.
registered since the.
Please vote. Please. Say
I've been registered since the primary.
yeah. Okay. Please vote. I wish I'd have known that. I'd have told my first class vote. I'd have told yesterday's classes.
Well, they got voter. Let me read you the email. Well, I mean, you don't even have any more classes today, do you?
Yeah. Ours.
You
Linear
can
algebra.
announce it to me in about 15
Yeah,
minutes
okay.
if you like.
Yeah.
But they have
But this is
something-
coming out on your Lawson email?
Yeah.
Okay, well then everybody should be hearing it anyway.
They have a registered vote on campus.
Oh, I see.
At
Okay.
the Kennedy Student Center in Birmingham.
Okay.
It's 10 to 3.
So this isn't the last day to register, or
No,
no?
it's just
Okay.
National Register Day.
Okay.
Everybody go register.
Okay. So they can still register tomorrow and Thursday. I hope. Well, I
I
hope
don't
so.
see why that wouldn't be.
Well, there is a deadline. I don't know what it is for Alabama. All right. So here's example 3. You got time to get it started? 4 minutes. Let's do what we can on it. Solve this. This looks different. Is it any different? dy dx is equal to xy squared minus cosine x sine x over y times 1 minus x squared, where your initial condition y of 0 is equal to 2. Okay. Doesn't look too promising, does it?
No.
But let's write it in differential form, which is dy is equal to, okay, wait, no, I'm going to change it slightly. Okay, yeah, okay, okay. Let's multiply both sides of this equation by y times 1 minus x squared. Okay, so this will be a y times 1 minus x squared. Okay, so this goes out here, and we'll write that in differential form, and that would give us y times 1 minus x squared dy equal, x y squared minus cosine x sine x dx, right? Now, let's add, and this is all one term here, let's add that, let's subtract it from the other side, which, note my sleight of hand here, that's going to make it, okay, well, here's what I'm going to do. Cosine x sine x minus xy squared dx. Notice I reversed this thing and added, or however you want to say that. Yes, exactly. Plus y times 1 minus x squared dy, and that's equal to 0. Now we've got it in our exact differential form, where this is your m of x, there's your n of x, m of xy, n of xy. Okay. In fact, rather than keeping that separate like that, I think it's probably better off to go on and do this, y minus yx squared. I think it'd just be a little bit easier when we do the thing, yeah.
So that first one's your m, the second one's your
Yes, this is now my m of xy, and this is my n of xy. Okay, and what's we got to do to verify first? Partial of m with respect to y, why not? And what would that equal to? Really? Those are all functions of x. So that's a constant. That's 0. It's turning out a little easier than you might have thought. Yeah, and this will be minus 2xy. Okay? Now let's do the partial of n with respect to x. And what will that equal to? Yeah. Minus 2yx. If you want to write it that way, it's fine. And those are indeed the same. Multiplication being commutative like it is, isn't it? So, we're fine. Okay? So, okay. All right, we'll pick up with this one. So this, I mean, it looks a little hairy.
It's not too bad. It's got some pretty solid, things to look for, and that sort of thing, and you can work through it pretty well.
Yeah.
I think this is less ambiguous than it started out being.
Right.
It started out pretty bad.
Let me. Where are we here? We've done that.
We're partway through example 3, right?
Yeah, I know, but I'm trying. Oh, here we are. We've done this, so we'll pick up right here. Okay. Thought I had it, but okay. And let's see, homework exercises. I think you can probably do some of the odds 1 through 19. And since we haven't finished the initial value problem, I'll hold off on that. So good deal. Okay. And I will end the